Hello, this is part two of our discussion on ketone bodies. And so I just want to summarize what we talked about in part one, and really about how ketone bodies work and why they function or why our body uses them during good times. And so if you're a healthy person. So normally what happens is at certain times you may be getting low on your glucose and your carbohydrates. And so normally we'd have glucose as it starts to be used up, so in between meals or other times, then we lose our glucose levels and the concentrations fall below a certain level. Well, then what happens is we rely on our stored energy in the forms of fats. Of course, lipases break those down into the free fatty acids and glycerol, and glycerol enters in through glycolysis, and then we use that all up. Then we undergo beta oxidation to form acetyl-CoA, and then the acetyl-CoA goes into the citric acid cycle. Okay, not a problem. However, at some point in time, if you don't intake additional carbs, you will start to use up and you'll lose all your carbohydrate reserves. And so then what happens is that we start to get, we start to scavenge from the citric acid cycle. So for example, oxaloacetate. So oxaloacetate will go on to go through gluconeogenesis to form glucose. Glucose can then be exported to be used as fuel. Then, as time goes on, we will run out, or we'll start to run low on some of the citric acid cycle intermediates. Okay, so acetyl-CoA will begin to accumulate. Well, there's a very limited amount of coenzyme A in your body, and your liver really needs to utilize it. So we need to be able to get the most oxidation out of this acetyl-CoA without expending too much coenzyme A. Okay, and so what we do is we do form ketone bodies. And so under normal conditions, small concentrations of ketone bodies are fine. The acetone gets expirated, or we exhale it, and then we can use the acetoacetate and the D-beta hydroxybutyrate to be exported for energy sources in places like your heart, your muscles, your kidneys, your brain, things like that. Okay? So that's what happens in the good times. And just remember that the liver cannot utilize the ketone bodies for energy sources. It has to rely on the lipids and the in glucose. All right, so there are times now we're going to focus on whenever the ketone bodies run amok or the concentrations get too high. Okay, and so it goes awry. The homeostasis goes awry. And there are two instances for this. Okay, predominantly one way can be starvation, and when we say starvation, we mean just a lack of nutrients. Many times we're talking about anorexia, bulimia, eating disorders, but you can actually be eating a large quantity of food and still suffer from malnutrition. All right. Another way to start to get higher levels and concentrations of ketone bodies is to go on extreme low-carb diets, especially for long periods of time. Okay, because you're just not getting enough of the carbohydrates, and so you're going to get the formation of the ketone bodies. Another large class of pathologies that can lead to ketone body formation is diabetes, when you have uncontrolled diabetes. And so now we're going to be looking at and comparing just starvation in general and then versus what happens with diabetes. So during starvation, the concentration of carbohydrates gets way too low. Okay? So now we're not talking about just normal fasting between meals. So what's going to happen here? I want you to start to use the logic and to think about what resources will your body tap into. Well, this is when the gluconeogenesis kicks in, okay? And it's going to make additional carbohydrates from the citric acid cycle intermediates and those glucogenic feeder pathways. But at some point in time, what will happen? You're going to deplete the citric acid cycle of these intermediates. The acetyl-CoA is going to accumulate. It's got to go somewhere. And so the liver's acetyl-CoA is going to be converted to ketone bodies, so that way the other tissues, especially the brain, the heart, things like that, can utilize these for energy. And for short periods of time or low concentrations, this is fine. It's a suitable energy source. But what will happen eventually? The extrahepatic tissues are not going to be able to keep up with the concentration of acetyl-CoA that is available. And so this concentration is going to get too high for this oxidation. So what's going to happen next is a disease condition or a pathology called ketoacidosis. Okay, and this is where the blood pH is going to drop due to the accumulation of these ketone bodies inside in your bloodstream. So, since not everyone has taken Organic Chemistry 2, some of you are currently in Organic Chemistry 2, and we haven't covered how ketones can lead to lowering the pH or increasing the concentration of protons, I'm going to go ahead and explain that here. Okay, so I'm just going to take a generic ketone, which has the characteristic carbonyl. Okay, and these ketone bodies, similar to acetone, or acetoacetate, I should say, they have a C alpha that has at least one hydrogen on them. Okay? Well, there's a special characteristic here. And that characteristic is this idea, or this ability, that the proton, or the hydrogen, I should say, that's hanging off of this C alpha is more acidic than what you would normally expect a hydrogen hanging off of an alkyl carbon to be. Okay? And that is because of it being adjacent to the carbonyl and the oxygen of the carbonyl group. So I'll show you what I mean by that. You can imagine that these two electrons can actually go, boom, sound effects optional, towards the carbon of the carbonyl group. And something has to break or give, and what can happen is the electrons of the double bond can actually flow towards the more electronegative oxygen of the carbonyl group. So essentially what you're doing here is this hydrogen can lose its electron. So it is just a proton, and it leaves. And by it leaving, it's going to increase the pH. It's going to increase the concentration of the hydrogens in the blood and decrease the pH. And so this is going to result in the following. Okay, we have what's called an enolate. And we have, I'm just going to draw it as a free proton, but we have this proton out there that's decreasing the pH. This can lead to a decreased pH of the bloodstream, which can be very, very deadly. Okay. So, this ketoacidosis, as I mentioned, it's a dangerous condition that your body experiences if you have to rely on ketone bodies for your energy source for too long. So how is diabetes different from starvation? So if you don't treat your diabetes, your concentration of insulin is going to decrease. So whenever this occurs, what's going to happen? Think about what's happening with respect to each individual cell's ability to utilize glucose and carbohydrates for their energy source. these extrahepatic cells cannot uptake the glucose for the fuel or take it for fat conversion. So what are they going to have to rely on? Okay? What's going to happen is the concentration of one of the intermediates, the melanoid-CoA, which is a starting material for fatty acid synthesis, it's going to decrease. And we're going to go over fatty acid synthesis in the future chapter. This also inhibits carnitine. Let me start again. This condition actually inhibits the inhibition or the decrease of carnitine acyltransferase. Okay, so what I realize that's worded kind of oddly. So what happens is as concentration of melanoid-CoA decreases, this condition is going to also cause what's normally carnitine acyltransferase 1 inhibition to be relaxed. So therefore, what's going to happen if it's no longer inhibited for carnitine acyltransferase? What does carnitine acyltransferase do? Well, just as the name implies, it transfers an acyl group to carnitine. So, this enzyme is going to transfer the fatty acids into the mitochondria, ultimately to be degraded into acetyl-CoA. Because now we have otherwise the fatty acids would have been out in the cytosol, but now since it's no longer, the transferase is no longer inhibited, they're going to be exporting them into the matrix of the mitochondria in order for them to be degraded down to acetyl-CoA. And so where does this acetyl-CoA usually go? It usually will enter in the citric acid cycle. However, since the cell is not getting glucose from the bloodstream, what's going to happen to the citric acid cycle? It's going to constantly be undergoing gluconeogenesis because it's not getting any glucose. If it constantly undergoes gluconeogenesis, you're going to run out of the intermediates like oxaloacetate, OAA, alpha-ketoglutarate, alpha-KG. So then this acetyl-CoA itself is going to accumulate, and it has to go someplace else. It cannot just hang around. Okay? What's going to happen is it's actually going to accelerate the formation of the ketone bodies, and it can do so quite quickly, and it goes beyond the capacity of the extrahepatic cells. So this too is going to ultimately result in ketoacidosis. And so this is just a cartoon depicting some of the issues undergoing in diabetic ketoacidosis. So if you either have insufficient or absent insulin, one thing is that the muscle cells will actually start to break down their proteins to release amino acids in order to get whatever energy they possibly can get, okay, for glucose. But even if the liver breaks it down for glucose and breaks down glycogen for glucose, the glucose is not going to be able to be taken up into the cell. See, the glucose production, it's kicking the glucose out there, but the extrahepatic cells can't take it up since there's no insulin or not enough insulin. Also, the fat cells, the lipases, are going to be activated since there's an increase in glucagon, and so it's going to create the glycerol that's going to go into for glycolysis, and glycolysis is going to ultimately gluconeogenesis, and gluconeogenesis ultimately going to increase the amount of glucose that's around. The fatty acid is going to be converted to ketone bodies, it's called ketogenesis, so there's going to be an increase in ketone bodies. And so you see this is a major issue because you're increasing the amount of glucose in the bloodstream, but that's not helping the extrahepatic cells to take up the glucose. You're increasing the ketone bodies in the bloodstream, which is going to lead to ketoacidosis. So some of these symptoms, one symptom is the fact that the breath is going to smell like vinegar or acetone. Okay? But you can actually have seizures and muscle weakness, diarrhea, because your body's trying to get rid of as much as it possibly can. You can have heart problems, gastric problems. And if you think about it, remember from last semester that due to the Bohr effect, one way that our body tries to control the pH is by the amount of carbon dioxide versus bicarbonate in the bloodstream. And so this can actually cause shortness of breath. Ultimately, you'll have headaches, confusion, you can lose consciousness, go into coma, and ultimately, if it's not treated, and it can, if you're diabetic ketoacidosis, or DKA, can be very quickly progressive. It can progress quickly and ultimately lead to death. Okay, so it can be fatal. Still to this day, it has about a 5% mortality rate, and even just recently, one example that I found is that Casey Johnson, who's only 30, she's one of the heirs of the Johnson & Johnson dynasty. She died in 2010 from diabetic ketoacidosis. So hopefully you can see how our bodies under normal circumstances can utilize ketone bodies in order to create energy. However, if this goes on for too long, and for instances of malnutrition, or if you have uncontrolled diabetes, it can lead to ketoacidosis and ultimately be fatal.